Our next speaker is Alisa Leavesley. It's from Thomas Keating Company, one of the partners of Peter project. In fact, this is a fully Peter talk. She will talk about the hardware behind Peter.
Hi, everybody. So as Monica said, I'm Alisa Leavesley, and I'll be talking about the hardware behind the Peter program. So just as a brief kind of overview, as a reminder, we're combining high field EPR with scanning probe microscopy techniques to try to localize the magnetic field at the tip of a scanning of a probe so that we can enhance our EPR signal. And so I'm going to do a brief overview of kind of the instrumentation and then go into a little bit more detail on them. So because we're doing high field EPR, we of course need a high field magnet, as well as just because of the structure of the system, we need to accommodate the microwaves coming in from above. So we need a support structure that will allow X, Y, Z and Z angle alignment for optimal coupling of the terahertz irradiation. We need terahertz sources, and then quasi optics to be able to direct and manipulate those sources to the center of the magnet. As Richard kind of discussed on Tuesday. We'll then also need some kind of insert to both vary the temperature. As yours mentioned, we need to, if we go to low temperatures, we can increase the sensitivity of our EPR measurements, and that also contains our scanning probe microscopy unit. We then also need our detector systems in this, and we have a couple of different options that I'll discuss later. So first off, if we look at kind of the magnet and the variable temperature, we have a cryogenics limited wet magnet. And so we chose to go with a wet magnet to try to limit the number of vibrations we had to deal with during microscopy. And this is a 12.1 Tesla magnet that's sweepable. And we needed an extra large magnet to be able to accommodate the scanning probe microscopy unit at the bottom. And we can go down to, I think it's about 4 Kelvin in this system. Then if we now look at our sources, there's 2 main options, both of which are amplified up to our ideal 320 gigahertz through a VDI amplifier multiplier chain, or AMC, but they can be driven by 2 different sources or synthesizers. One is a YIG-based oscillator, and this is great for continuous wave or slow frequency sweeps, and it allows us a lot of different options if we want to go to a different frequency band in the future, but it does have a low power output of only about 1.4 milliwatts and needs to be paired with our bolometer. Alternatively, we have a high power option, which allows us to get about 55 milliwatts of power. And this is driven by an arbitrary waveform generator, or AWG. And this is great if we want to try to do pulsing or potentially fast frequency sweeps, which is very advantageous when we want to try to actually do a microscopy scan so that we can take a full EPR spectrum at every single pixel. And here we can then also either use a bolometer or say a heterodyne detector for the system for detection. One thing we have to be concerned about with the arbitrary waveform generator is we were using a Tektronix 7001A AWG, which actually allows us to produce the base frequency we would ideally need to drive the VDI AMC, which is 13.3 gigahertz. Unfortunately, in order to make sure we're not going to alias the signal that we're generating, we would need to take 2 to 3 times the number of, we need a sample at a rate of 2 to 3 times that, which means we would need a sample at a rate of approximately 40 to 50 gigahertz, or gigasamples per second. And this means that we would then have very large memory requirements for any kind of waveform we would generate in the system. So to reduce that, we can do something called sample imaging, where we're going to have our base frequency at, say, about 3.43 gigahertz. And here I'm just showing a 500 megahertz linear frequency modulation. And then we use a sampling rate of 9.9 gigahertz. And then we can look at the sample image where we're actually doing the addition of the 2 to get our desired output. But because we don't want all this other junk to be kind of amplified up by and influence our AMC, we can just use a simple bandpass filter to only look at our desired frequency range. So just to kind of show some of the performances we can do in just looking at the frequency range, these are just 1 microsecond pulses, looking at if we have a rectangular monochromatic pulse versus if we have a rectangular pulse that has a 500 megahertz linear frequency modulation, or if we're looking at, say, a hyperbolic secant pulse. We can then, that's at a monochromatic frequency, we can then look at what kind of frequencies that we'll actually be hitting. So we can then have very good control at the nanosecond regime of what frequencies we're actually observing. So once this AWG is then put into the VDI AMC, we actually have a very consistent power output across our entire 12 gigahertz bandwidth for this high power system. And that's the main limitation of this high power system, is that we only have this 12 gigahertz bandwidth, which does limit some of the applications we can look at to approximately looking right around where the G is equal to 2 for EPR measurements. So now to translate our terahertz radiation from the VDI AMC to free space, we'll use our ultra Gaussian horns that we manufacture at Thomas Keating. And these typically have, at this frequency range, approximately 1 dB of loss, or a little bit less than that. And this is critical, especially if you're using, say, one of the low power sources, that we minimize how much losses are in the system to maximize how much power is actually being able, is reached at the sample position. So as Richard kind of went over some of our quasi optics on Tuesday, I'm going to walk you through a little bit of the specific optics for the Peter project. So once we have our terahertz irradiation coming out of our source, we can then have it sent off to one of our wire grid polarizers in the system. And these are key because they allow us to act as both a polarization selector as well as an attenuator in the system if we want to be able to vary what the power we're sending to the sample. And so from there, we can then go through another wire grid polarizer, and then we have a Faraday rotator in here, which will rotate our polarization by 45 degrees. And then we use a focusing mirror to refocus the microwaves down through another wire grid polarizer into a corrugated waveguide in our insert to direct the microwaves down to the sample position at the sweet spot of the magnet. Now, a thing to remember in our system is that the antennas on our probes are only active if the electric field of the microwaves are aligned with the length of the antenna. And so this will be our active state, and if they're perpendicular, they'll be inactive. So we need to make sure we can tailor the linear polarization of our microwaves to match that of the antenna that's actually in the scanning probe microscopy unit. So to do that, all of the wire grid polarizers in the system, which are denoted by these little asterisks, are rotatable so that we can then tune the polarization to meet that of the antenna. Since these are all custom-made antennas, trying to get them to be perfectly aligned with a set polarization is a bit more challenging. So this allows us to kind of tune the system appropriately. So now once the microwaves are inside of our corrugated waveguide, we can then direct them down the length of our insert down to the scanning probe microscopy unit, which consists of the actual probe, which was discussed, the simulations were discussed by Martin on Tuesday, and then they'll also be discussed by a different Martin afterwards, after my talk. We then have a sample stage, which comes in from the side, and then the terahertz beam path, and the movement stages are underneath it. So the actual probe itself is kind of shown here. And if we go for a little bit of a close-up, we can actually see this is our sample stage. We've got our scanning microscopy probe unit here, and we have then the waveguide coming down and the movement stages underneath. I'm going to speak a little bit more about the terahertz beam path since that's where my expertise is. And so we've got two different kind of main approaches. We have an approach where we're going to come from below, and we're going to have an approach where we come from the side. And so as we've shown here, with the first mirror in both instances is an elliptical mirror, and then we have a hyperbolic mirror underneath to be able to ultra focus the beam path. And so here, this beam waist is the radius that's containing approximately 86% of the power. And at this point, this is about one wavelength at 320 gigahertz. So we can see that our whole beam diameter is about 2 wavelengths. So we can't get too much with just normal optics for focusing. This is about the limit of what we can achieve. So we also wanted to look at what's kind of the analysis, what losses and noises will contribute to the system. And so effectively, the higher the number, or the lower the number actually, the less loss we're getting in the system. And although approach 1 is slightly more lossy and will contribute more noise to the system, this is the main approach we've been using for all of our measurements, just because it's a little bit easier to implement. as well as the fact that, and the reason the losses are a little bit higher is because we have a slightly smaller beam size compared to approach 2. So once the beam has then come up through our sample stage, which has the optical access, goes through our sample, it can then interact with the tip that is coming from above. And then any EPR signal will have to come back through, be reflected back off of these mirrors, and then we'll recouple into our corrugated waveguide. If we're going to just do a simple EPR measurement, we can then put a flat reflective surface over top of the sample here, and it will just cause straight back reflection if we're just doing a simple EPR measurement instead of a microscopy measurement with the SPM. Now, if we're doing EPR, we need to modulate the magnetic field. And so we're using a Helmholtz coil for this. And so that's so that we can partially, because of the large sample volume, this is approximately 89 millimeters across, which is quite large, which is partially why we went with the Helmholtz coil design and for the sample access. One of the disadvantages of this particular design is that it requires a fairly high current requirement to be able to get any kind of significant magnetic field. And this causes quite a lot of heating. So one thing we're working on is we've actually got a 2nd generation probe that's in testing right now, but I don't yet have those results. And this to reduce the heating effects, as this affects some of the performance of the system at cryogenic temperatures, which will come up in a little bit later. So now that we've got our signal, our EPR signal back into our corrugated probe, it will come back up. And as Joris mentioned on Tuesday, very nicely, that once the microwaves have interacted with the sample, there are 2 components, or the light is elliptical, which has then components that are copolar, which are parallel to that of the incident beam, as well as those that are perpendicular, which are our cross-polar signal. And so we can detect both in this system, and I'm going to kind of walk through how we can get to either of those options. So if we look at first the copolar signal, because it's got the same polarization as the incident beam, it will go through this wire grid polarizer and then be rotated a further 45 degrees by this Faraday rotator, which will cause it to be reflected off of this wire grid polarizer. Then from here, we can then, depending on the wires at this position, we can direct the microwaves to either detector port, this detection port, or this detector port. And then in these positions, they can either be a bolometer, a heterodyne detector, or either other detection methods, such as a zero bias detector, or say even our Thomas Keating terahertz power meter. Then if we look at the cross-polar signal, because it is perpendicular, it will be reflected off of this wire grid polarizer and sent in this sort of pathway here, in which case it can only be directed to this detection port, which will primarily either be a bolometer or a heterodyne detector. So our primary detectors in this system will either be a QMC hot electron bolometer or a custom-made VDI bolometer that's paired to run off of the AWG. So that same AWG that would be driving the AMC at the beginning will also be used to drive this heterodyne detection scheme, which allows us to then also obtain both the magnitude and the phase instead of just the magnitude for more traditional EPR measurements. So kind of our first measurements we need in the system is to confirm that both the SPM unit is working as well as that EPR is working separately before we actually look at the combined Peter measurements. So kind of our first microscopy measurement was that if we took a roof mirror, which will allow us to be able to rotate the polarization of the beam coming in and apply it to stick it to our sample stage, we just kind of did a cross-polar measurement of what is the beam pattern coming off of this roof mirror as sort of a proof of principle that the movement stage is working within the magnet. And that can we couple it properly to the optics, and what can we observe in the system? So this was kind of our first image that we acquired on the system at all. And then if we look at some of the initial EPR measurements, Joris presented this manganese 12 as a good sample system. So using the high field EPR system that they have in their lab with their bolometer, this is on their standard EPR system. We kind of took some reference measurements at 10 and 20 Kelvin. And then we replicated those same measurements using the same bolometer in the Peter magnet with our Peter optics and using the sample stage in the SPM. And you can see that we can get EPR signal, which is great. but that the temperatures don't match up with what are recorded. It should be noted here that the temperatures, not all the temperature sensors were installed at this point when this measurement was taken, which they've now been installed, so that this was only looking at the temperature at the insert from the variable temperature, at the port of the variable temperature insert, rather than actually at the sample stage itself. And this heating effect that we're seeing of 10 to 20 Kelvin is due to the modulation coil, which is why we're going to have the second generation modulation coil to try to reduce that heating effects in the system. So you can see that right now, kind of our 5 Kelvin is a better representation of what's actually happening closer to 20 Kelvin. So we're off by approximately 10 to 15 Kelvin. We also then tested the heterodyne system on the main magnet in Joris's lab, the high field EPR system, rather than the Peter system, due to a slight issue with the magnet power supply on the Peter magnet. But we can clearly see nice EPR signal in both the I and the Q channels of our heterodyne detector, which is a great kind of first start to be able to see EPR in both of those systems. So overall, I got to thank our my collaborators at Thomas Keating, specifically Dr. Kevin Pike, Dr. Richard Wild, and our CAD designer, George Sabak, the team at the University of Stuttgart, specifically to Dominic Blos, Lorenzo Tessi, and Martin Kunetschi for their help with their system and having me kind of direct them remotely from COVID, as well as installing the system and testing it out. The team from the Brno University of Technology for the development work on the SPM, and Rainer for discussions regarding detection and modulation. And so this is right after we got the magnet when it was first arrived in Stuttgart. So that was quite an exciting day. And I've got to include one last photo that was a bit fun from when we were installing the support unit and the optics. This is not how you should normally align your optics, but this is how we did it for the first day. So if there's any questions.
Okay, thank you very much, Alisa, for a very nice talk. Now it's time for questions. So, Sasha, please go ahead.
Yeah, a couple of quick questions. Thanks for the talk. It's excellent overview. What are the pros and cons, let's say, or what are the advantages of the side illumination scheme?
So the advantage of the side illumination scheme is that you could potentially reduce the amount of the backscatter that you would get from the tip. And then so you could potentially have less noise in the system. However, because we're modulating using the modulation coil, so we should only be looking at signal that is actually coming from the actual EPR signal, especially when it's been demodulated after detection, but it could help reduce with the noise. I
see. And how are you planning to reduce the heating? Are you still sticking with the Helmholtz coils?
Yeah, so we still sticking with the Helmholtz coil. What we've done is we actually we changed the design a little bit, so we reduced how much access there was to the sample, and kind of made the coil larger overall. So we were able to kind of redesigning it and figure out how we could maximize the space of the coil. We were able to increase the number of turns by a factor of 3.5, so that should reduce the amperage requirement by a similar amount, and similarly reduce the heating effects.
Got it. Thank you.
Mm-hmm.